Hello, this is a test device that I've put together, and hopefully you've watched the previous video to get a better idea of what the principle of this permanent magnet motor is. And it was designed by me, and I'm the inventor. And the idea behind this design is that it's a motor or solenoid, or it could be used for a speaker. And what it uses is the flux of the permanent magnets to create a lot more work instead of more electrical power. So this design uses a very small amount of input power, and compared to the amount of mechanical power it can deliver using the permanent magnets. So as you saw in the other video, here I've got the magnet poles written. So there's our center core, and we have our two north magnets facing down here, and our south poles are on the opposite outside cores. And the magnet configuration that you see here is identical on this side here as well. So that is the basic principle of this, and we will demonstrate to you how much power the permanent magnet motor, the mostly magnet motor here, can deliver in pulling force with a certain amount of input voltage and current compared to what a off-the-shelf speaker can do. This is a 25-watt speaker that is a woofer that has been pulled out of a 52-inch plasma TV. I have two identical ones. This one's been modified and attached to a scale, which the scale is going to measure the amount of grams of pulling force once we apply a voltage. This has a 8 ohm DC resistance, 740 microhenries of inductance, and this coil here is not great comparison because it has a lot of resistance, but that's fine. It has a lot of power, so there'll be no problem doing a comparison. We have 40 ohms DC resistance, 250 millihenries of inductance, and it's a very fine wire that's wound on this one here. So we also have the identical scale that's here, hooked up here, so that it could measure the pulling force of this, and we'll do the comparison of grams per watts that is consumed. So without further delay, on this meter here we have our voltage, and now no current is applied because it's not connected yet, but we'll take our reading once we do that. And now it is connected. Oops, sorry, I forgot to turn on this first. So as you see, we have 0 grams right now, and now I'm going to apply the current, and we have 165 grams of pulling force there for 3.11 volts input and 414 milliamps. So that's a 0.413 is our milliamps, and there you see the 165 grams. I've already written that, and we'll look at that data next. And now I will apply that same voltage to the mostly magnet motor, and this time I'll think of turning on the scale there. And now I will, so as you see, we're at 0 there, and I will apply the connection, and we're getting 515 grams of pulling force there, and we're utilizing 4.1718 volts at 103 milliamps. And we'll disconnect that now. I'll shut these off. Now, if we look at our data, this is what our speaker has performed at 3.10 volts. That's when I had done it previously. We have 413 milliamps. This comes to 1.28 watts. We had 165 grams of pulling force for that 1.28 watts, which means 0.00776 watts per gram of pulling force. And here's the Moseley magnet motor, and we had 4.19 volts at 103 milliamps, 0.432 watts, 432 milliwatts, and we got 500 grams, or it was even more than that, 515. It varies between 5 and 515. We'll just put it at 500. So it gives us a total of 0.00086 watts per gram, which means this Moseley magnet motor with the same amount of power, well, in the same voltage range anyways, without changing the voltage, has 9 times the pulling power per watts that this off-the-shelf speaker has. And this demonstration is just to show that if this would be utilized in a speaker configuration, you could use a very small amplifier to produce a lot of mechanical movement compared to a traditional speaker, because this has not necessarily been designed to utilize mostly the magnet force, where this has been designed to use mostly the force of the permanent magnet, so that very small amount of power is required to move this. So for very large speakers, I would say that you'd be able to displace some very low frequencies of strong mechanical movement with a very small amplifier compared to what you can do with that. That would be, I would say, the most advantage for utilizing this technology in a speaker. Now, this can also be used in a solenoid, and the advantage that this has compared to a solenoid is a solenoid, as it moves the actuator, the plunger inside the solenoid, as it moves away from its resting point or going towards its resting point, it doesn't have the same pulling force, so it's not linear. Yet this one here, there is no difference between the pulling force from this point over to this point. So this has a half-inch space here, so it can move half-inch that way or half-inch back the other way. And this one here has no difference in pulling force anywhere it travels across its dimension here, its stroke back and forth. So pulling force is always equal. The other thing too, that this could be used in a motor possibly, and it would have to have a crankshaft to use its action. It would have a huge amount of torque, and for a small amount of input power, so a lot of mechanical power. And the interesting thing about this that it has is there is zero cogging. So because it is the movement of the coil that's within these cores, then there is zero cogging. Plus the other effect that it has compared to a permanent magnet motor or DC magnet motor is that once you move the coil as well, the inductance has zero change, or next to none anyways, as you move it along. The inductance is the same, the pulling force is the same, so everything is very linear. There is no changes in there. There are some other advantages, but anyways, those are the main advantages of this design. Now, the next thing that I'll do is I'll hook up this speaker here to a signal generator, which has a very small output, but we can see movement in the speaker. And I will hook it up as well to the Moseley magnet motor, and we're going to do a comparison of, you know, just by hand you can feel the mechanical power. So I'll detach it from the scale and use this one here, because that one's attached to that scale permanently. And we can also look at the oscilloscope. I have an oscilloscope hooked up to my laptop, and we're going to look at the two. So that'll be in the next video, so have a look at the next video for seeing the results of that.